Right. So anyway, so the trefoil knot is one of the simplest. There's another sort of maybe the next simplest knot is the figure 8 knot. Figure 8 knot, and what it looks like is you kind of you start off with something like this. Let's do something like a figure 8, okay, and maybe just okay, so something like a figure 8, and then you kind of imagine this is going here, this is going here, this is going there. Okay, and it turns out this is another common knot that one sometimes ties. Okay, again, so you can think of this as a circle kind of sitting inside R3 in a slightly different way, right? And the point is that these three are, and there are different knots. Okay, so I'll show you a table in a little bit. But the point is that we say that two knots are the same, are topologically equivalent in some sense. So we say that two knots are equivalent. So two knots, let's call them K1 and K2, are equivalent if there exists a homeomorphism, let's call it capital F, from R3 to R3 that takes such that it takes one knot to another, so such that F of K1 equal to K2. Okay, so so we'll take, for now, we'll take this as a definition. So let me actually make a sort of some kind of remark that it's the same. So sometimes this is expressed as the following. So sometimes we want a continuous family of homeomorphisms that starts in one knot and ends up in the other. So a continuous family, let's call it capital F T. This T goes from, let's say, 0 to 1. T belongs to 0 to 1, such that at F of 0 is the identity map, and F of 1 takes K1 to K2. Okay, so so you can view this as a movie, right? So one knot kind of sort of deforming continuously to another. Okay, so this is, if you can do that, then these two knots are the same. So for example, so if you take something that looks like this, if you take something that looks like this, okay, so then you can definitely, you know, this call it K1, and you look at sort of this unknot. So this guy is definitely, you can, you know, so you can imagine you're just sort of twisting it so that it becomes an unknot, right? Here's a more sophisticated example. So let me, this is from Wikipedia. This is an example of something which is an unknot. Okay, so initially it's a very complicated, looks like complicated. It has many crossings. It looks complicated, but then you can, you know, deform it, as this movie shows, to the unknot, right? So this is equivalent to the unknot. Okay, and so the so let me go back to. Oh, by the way, so let me show this right away. So here's a table. So these kind of understanding. So the basic problem in knot theory is to sort of understand when two knots are equivalent and when they're not. And this understanding sort of knots, classifying knots up to equivalence is has been sort of studied for, you know, more than 100 years and 150 years perhaps, and sort of people have all these tables of knots. So each, you know, two knots in this table are different knots. Okay, so they cannot be, you know, sort of you cannot have a homeomorphism one to the other, and so on. So this is the basic problem in knot theory. Right. So the basic problem in knot theory is when are two. So let me write it in different colors. So basic problem is when are, how can you say, so how can you say if two knots are equivalent. Oh, by the way, I forgot to, when I said it as a remark, but this definition of continuous family of maps is actually the same as the previous, the definition I gave. Okay, so if it's as good as, you know, wanting one homeomorphism from R3 to R3 that takes one map to another. I mean, whenever if you find such a homeomorphism, you can actually, so you can connect it up with the identity map with a continuous family of homeomorphism. And another remark is, I should add over here, is that you sometimes want, actually when you actually do knot theory, you always want this F to be orientation preserving, whatever that means. Okay, so I'm not going to go into that. So it turns out that you don't just care about whether there is a homeomorphism, you care about whether, so sort of somehow, so which direction, so some sort of X, Y, and Z axis, you want to sort of preserve the orientation, the left-handed or right-handed orientation of the X, Y, and Z axis. Okay, so so in any case, this is the basic problem. So if you are given two knots, can you tell whether they are homeomorphic or equivalent in this sense? I mean, they are of course homeomorphic as topological spaces, right? They're both S1, but whether the ambient, there's some homeomorphism R3 that takes one to the other. This is the sense of which knots are equivalent, right? So so again, once again, just like the basic problem of topology, so you need knot invariance, right? So you need sort of need some kind of invariance. Let me just call it knot invariance. That so these are numbers perhaps attached to a knot, so that if two knots are equivalent, then they are they have the same number, that same not invariant. Okay, so this is sort of the whole game, and then so this is sort of a I mean, so let me just say it's an unsolved problem. This basic problem is unsolved, so there's no complete set of knot invariance is known. It's still an unsolved problem. There's nothing like, you know, sort of just like the basic, you know, sort of classification of surfaces. There's a theorem. If you know the Euler characteristic and orientability, and then you know what surface you are. Here, there is no such theorem. Okay, so this is what topologists. This forms a good playground for developing concepts in topology that are useful in other contexts as well. Okay, so if it works for, you know, this problem, then it is a good chance of working in many other, you know, classification problems in topology and attacking the basic problem. So this problem in knot theory is sort of like a good test case for the bigger problem, the basic problem in topology. Okay, so let me just tell you about one invariant, because we have been kind of you know, talking about things which are similar. So one invariant is called embeddability. Okay, so is one invariant is the, let me call it the embedding number. I don't really know what, I mean, people in general call it. This is not a very commonly used invariant, by the way. So you can, if you look up, I mean, let's say Wikipedia, etc., you'll find various invariants mentioned. So there are many knot invariants. None of them are complete. They can't really distinguish between any given pair of knots. Okay, so or they're not known to be complete, at least. Okay, so so one is called the embedding number. Let's call it n. So we say that a knot, let's call it k, has embedding number n. So let me call it embedding number n if it can be embedded in a closed orientable surface of genus n, which means that Euler characteristic, Euler number in the genus are related to 2 minus 2n. Okay, and cannot be embedded anything less than that. Okay, so embedded in a genus n minus 1, because the smallest genus surface on which you can put that knot. Okay, so let me show you a picture. So okay, so first of all, let me tell you that so example, if you look at an unknot has, so embedding number, so let me call it E number just to, so that I don't have to write it. So E number 0, right? Because you can embed it. Here's the embedding of an unknot on the sphere. Sphere is genus 0 surface, right? It's Euler characteristic, all the numbers 2. So you can put the unknot as an equator, right? So that's the unknot, and you're sitting inside on a sphere. Okay, so the E number of an unknot is 0. And in fact, so let me tell you the fact is that if you, so fact is that E number 0 means that it's a E number of k. Let me write it as E of k. Okay, so E of k equal to 0 means that it's an unknot. K is homeomorphic, so k is equivalent. Let me do some other notation for equivalent. Let's say k, this thing is unknot. Okay, so because it turns out, this is a theorem in topology. If you put any curve, embed anything on a sphere, then it bounds a disk. Okay, this is called the Jordan curve theorem. All right, this is another theorem that you learn in topology, maybe towards the end of the first course in topology. Okay, and so using that, you can show that, so if you embedding number 0, then you are the unknot. So at least it distinguishes the unknot. Okay, but can't quite distinguish between this other knot. So let me tell you the trefoil knot. The trefoil knot has E number 1. Okay, so you can embed something, a trefoil knot in a torus. Let me show you a picture of that. Once again, this will crash, I suppose. Right, so this is a picture of, this is again, just did Google image search. So this is, yeah, so as you can see this, so this is a, if you think about, the trefoil knot, you can sort of imagine it sitting on a torus. Here they've thickened the trefoil knot so that it looks like a rope. So you can put it on a, the tire tube or something. Okay, and this is called a torus knot. These such knots which can be put on a torus are called torus knots. So the trefoil knot is a torus knot, and torus is genus 1. Okay, so Euler characteristic 0. So that so this embedding number therefore is 1. So it's your genus 1 surface. So it can't be embedded in 0, 0 surface, because it turns out, I mean, the trefoil knot is a non-trivial knot. There's no way you can, unknot it and make it an unknot. Okay, so that continuous deformation. So it can't be embedded on genus 0 surface, but it can be embedded in a genus 1 surface. And that, so let me say that E of the trefoil is equal to 1. Let me tell you, so these are facts. Okay, so I'm not proving these. So these are things that it follows when you sort of read a little bit more topology. And it turns out that the figure 8 knot is not a torus knot. It can't be embedded in genus 1 surface, but it can be embedded in genus 2 surface. And I leave you to figure this out. I mean, I didn't really search for a picture, but maybe there isn't one. It would be nice if one of you kind of emailed me a picture of sort of figure 8 knot sitting on a genus 2 surface. Okay, genus 2 is, if you remember, surface of genus 2 is 2 holes, right? Its Euler characteristic is -2. Okay, so you can put a figure 8 knot on this, but you can't put it on a genus 1 surface. So this embeddability is is an invariant. But why is this? So I didn't talk about this. Why is it an invariant? Because once you embed it on some genus surface, if you have a homeomorphism of R3 to R3, okay, so then the surface will go along with it, right? So the image of this knot also sits on a surface of genus G, right? So it's by definition, it is as an invariant of this under this equivalence of knots. Okay, so it's clearly some invariant, and it's but it doesn't distinguish between knots. There are different. I mean, there are different knots sitting on a torus, right? All for which sort of have embedding number 1 because they're sitting on a torus and they're non-trivial, but they're not equivalent to each other. So it is not a complete invariant, but it is one invariant of knots. And there are many others. And as you progress in topology, there are more and more sophisticated invariants. And there are invariants which have been discovered around, maybe around 20 years ago. So it's an active topic, and things which are being sort of proved about it even today, and it's a very active topic in topology. All right, so anyway, so I'll stop there, and if you have any questions, I can take it now. This sort of concludes our sort of introduction to this subject. I hope that this kind of inspires you to sort of read up more, and there are many good sources, and I hope that you'll enjoy the process.